Okay, so welcome to this physiology tutorial. We are going to learn about genesis of membrane potential. Okay, so my name is Oscar Tembo. I do physiology tutorials, and if you haven't subscribed to my channel yet, you can actually hit the bell and and at the end, don't forget to like the video. Okay, so we just started in the previous chapter to look at what excitable tissues are. And today we are mainly going to focus on the genesis of membrane potential. How is the membrane potential generated? Okay, so as we all can see this diagram, the curve here. So the membrane potential, okay, I said excitable tissues are capable of generating membrane potential. And those are the nerve tissue and the muscle tissue. Okay, now what really happens, this is just a summary diagram of how membrane potential is generated. Okay, so physiologically, the normal membrane potential across a cell, which is the cell membrane separating the intracellular and the extracellular fluid, the normal the normal ions, they are at equilibrium inside. Let me draw this. At this point, all cells are at rest. Okay, so before anything is generated, let's use this as our reference for cell membrane. This is ECF or outside, then this one is inside. Okay, this will be our reference. So the upper one is outside, the inside is the inside. So normally a human being contains more, the cell physiologically, we have more sodium outside the cell and we have more potassium inside the cell. Outside the cell is more positive, inside the cell is more negative. We can look at this perspective. Outside the cell being more positive, inside the cell being more negative. If you are getting me clearly, I'm using the word more, meaning that inside it is negative, it is positive, it's both negative and positive, but dominant. The one which predominates everything inside is negative, and the one which dominates outside the cell is positive. Now, what happens is that at rest, the resting membrane potential cell of a neuron is about -70, as demonstrated here. -70 millivolts. At this point, there is no activity between what is happening inside the cell and what is happening outside the cell. But there are what we call leak channels across the cell membrane, on the surface of the cell membrane. They start allowing sodium to leak slowly inside the cell. This sodium is changing the membrane potential. Okay, it was -70, but sodium is rushing inside and is positive, meaning that it's moving this potential towards more positive, more positive. Okay, at this point, it has resting membrane potential. The membrane potential is -70 millivolts. But after the leak channels have started allowing sodium to enter, the membrane potential have started slowly increasing until it reaches -55. At this point, we call it the threshold. What happens at the threshold? At the threshold, we have, once the membrane potential reaches the threshold, there's what we call sodium voltage gated channels. They open, allowing more sodium to enter inside the cell. That's also called sodium influx. Sodium influx. So sodium influx will cause an overshoot. The threshold is reached, sodium voltage gated channels open, sodium rush inside the cell. It causes an overshoot because it has become more positive now inside the cell, is now more positive as compared to outside. Overshoot reaches about positive 40, I mean. At this point, the cell is more hyper positive inside. But what happens is that whenever it reaches negative positive 40 millivolts, the body physiologically crosses the channels of voltage of sodium. The voltage gated channels for sodium crosses. To this point, what get to be open is the potassium voltage gated channels. We all know that potassium is inside here. The potassium is inside here. But potassium now, once the potassium voltage gated channels open, it starts allowing potassium to move outside the cell, because potassium always moves outside the cell, unlike sodium, which moves inside the cell. Now look, inside is positive, potassium is also positive, but it's moving out. So at this point, potassium is moving out, meaning it's making inside the cell less positive, because it has started moving out in as much as there is already sodium, but potassium is also moving out the cell. So as potassium moves outside the cell, due to the opening of potassium voltage gated channels, once the membrane potential reaches in positive 40, it keeps on reducing. This is what we call repolarization. Reducing. Repolarization is due to the opening of potassium voltage gated channel as potassium moves outside the cell, making inside more negative. Are we okay there? But what happens is that the potassium voltage gated channels have a unique feature, and that is it takes time to cross. The potassium voltage gated channels takes time to cross. Therefore, before it reaches, before it realizes that it has reached the resting membrane potential, which is negative 70, which is a negative 70, what really happens is that since they take time to cross, they keep on moving more potassium until the cell reaches somewhere about negative 90, because the channels closes slowly for potassium voltage gated. At this point, the cell is said to be hyperpolarized. Hyperpolarization is due to slow closure of potassium voltage gated channels. Slow closure of potassium voltage gated channels causes hyperpolarization in a neuron. Okay, now we need to return this membrane potential back to negative 70. And what are we going to do? There is specifically a pump which is called the sodium potassium. Okay, sodium potassium ATPase. So what does the sodium potassium ATPase do? The sodium potassium ATPase pumps about 3 molecules of sodium outside the cell and pumps about 3 molecules of sodium inside the cell and 2 molecules of potassium outside the cell. So this sodium potassium ATPase, it pumps about 3 molecules of sodium entering inside the cell and 2 molecules of potassium going outside the cell. This is going to balance, diverting the hyperpolarization back into the resting membrane potential, because sodium will keep on boosting the inside, whereas we are losing some potassium. Okay, so this is all about the genesis of membrane potential. Let's hope it was clear. Just to summarize the process, at rest, they say the resting membrane potential is negative 70. Once there is leak channels, on the surface of cell membrane allows sodium to enter until it reaches a certain threshold where the sodium voltage gated channels tend to open, allowing more sodium to enter inside the cell. Okay, then since more sodium has entered inside the cell, this phase is called depolarization. Depolarization meaning inside is more positive. Now, once depolarization phase has been reached, and it has reached the membrane potential has reached positive 40, the sodium voltage gated channels needs to close at this point physiologically so that the process does not prolong. Once the sodium voltage gated channels crossed, the potassium voltage gated channels open at this point to allow sodium to leave the cell so that it can become more negative. Okay, then this process is the repolarization. Repolarization is just potassium potassium voltage gated channels open to allow the cell to return back to the resting membrane potential, hence repolarization. But since there is hyperpolarization, what causes hyperpolarization is because potassium voltage gated channels tend to close slowly, therefore they take time. The cell becomes more negative because potassium is leaving. Then what happens after everything has happened? The sodium potassium ATPase pumps 3 molecules of sodium inside the cell, 2 molecules of potassium outside the cell. This is the physiological process that revert back and brings the voltage back to the resting membrane potential. Hello guys, thank you very much for watching this video. Remember to subscribe and like the video as you await for more of these. Thank you for watching.